Thanks for watching this sixth video in a series of work solutions for Paper 1 for Edexcel GCSE Computer Science. In this video, we're going to be working through how to get to the answers for question 2b, so all about 2's complement and binary denary conversions. And your challenge at the end is to have a look at and have a go at question 2c, which is about run length encoding and Caesar ciphers. So let's remind ourselves what 2b looks like. If we read through the question again, so it says the drone's altitude, that's how high above the ground it is in meters, is stored using 8-bit 2's complement. When testing, it seems to work fine with heights of anything from 0 up to 127. But as soon as it gets bigger than 127, 128, the remote control seems to think that the drone has crashed, even though it seems to be working fine otherwise. It's within range and flies normally. So you get 1 mark for saying how you could store the altitude differently to avoid this problem, and then 2 marks for explaining why this problem is happening. We're going to tackle why the problem is happening first, and then go back to how we could do it differently to avoid it. So if we take a look at the answers first, and then explain them and see what they mean. So you could have any of these answers, or any sensible answer that means the same sort of thing. First of all, a value larger than 127 is not possible with 8-bit 2's complement. Let's have a look at 8-bit 2's complement and see what we mean by that. You might remember with 2's complement, if all of the bits are set to 1, the value is -1, rather than, if this was a positive number, that would be 255. So why is that? Well, 2's complement works in exactly the same way as positive binary, as in the least significant bits on the right is worth 1, and as you go to the left, each bit doubles, just like positive binary, but the most significant bit on the left, instead of being worth 128, as it would be in positive binary, it's now worth -128. So that means if all the bits are 1, you would do -128, add 64, add 32, blah, 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 which gives you -1. Why is that important here? Well, 0 is the same in 2's complement as it is in positive binary, it's just all zeros. 1 is the same, 2 is the same, 3 is the same, and all the numbers are the same until you get to all of the bits other than the most significant bit, the one on the left, being 1s. So everything up from 0 to 127 is the same. If we try and get a number bigger than 127, that would be 128, which with positive binary would just be 1 and then 7 zeros. But let's see what happens. If we press plus here, we get the 1 and 7 zeros, but that 1 isn't worth 128 like it would be with positive binary. It's worth -128. So our drone would think it's gone, if we say this is the ground, it goes up to 100, 120, 127, but as soon as it goes up to 128, the drone's still in the sky, but the sensor reading would be interpreted as though it's suddenly gone underground. So it's a limitation of 2's complement that it has a smaller maximum. The maximum value you can have for 8-bit 2's complement is 127. That's why the problem's happening here. So how can we represent that in a way that would get you the marks in an exam? And I do think this is a mean question. I don't think you'd get something like this. Well, I hope you wouldn't in the summer exam, but it's worth going through so that we understand how 2's complement works. So a value larger than 127 is not possible with 8-bit 2's complement. The sign bit will be incorrectly set to a 1, so the sign bit in 2's complement is the most significant bit, the bit on the left. And if the number is positive, the sign bit is always 0. If the number is negative, the sign bit is always 1. So the sign bit will be incorrectly set to a 1 for a larger value than 127. And that large value, as in the number bigger than 127, will be incorrectly interpreted as a negative number. Or you could say, remember, you only need to say any 2 of these. The most significant bit in 8-bit 2's complement is worth 128. If you write that down, you get 1 mark for that. Or if the most significant bit, MSB, is 1, the drone will think it's underground because it will be a negative number. So any 2 of these. So once we've explained why, we can think, well, how could we store it differently? There's 2 ways. Either we could use more bits, so we could have, 9 bits would be enough. or if we had more bits in here, we could go up to 128, and that would be absolutely fine because the sign bit is all the way over here. So you could have more bits, 9 bits, 10 bits, 16 bits, whatever. Anything bigger than 8 would get you the mark. Or you could say you could represent it using not 2's complement, as in positive binary numbers, because the altitude in theory should be less than, the altitude should never be less than 0, should always be a positive number. Okay, so I think that's possibly the hardest question in the paper. If you survived that, well done. Let's move on to part 3. The drone also has a sensor which measures the battery life as a percentage from 0 to 100. State how many bits are needed to represent this percentage and give a reason for your answer. So we need a number from 0 to 100, 1 mark for the number of bits and 1 mark for the reason. So let's have a look. We go back to just 8 bits, just go positive numbers because this is a percentage, as in it doesn't go below 0. If we just have 4 bits, the maximum number that 4 bits can store is 15, or 2 to the power 4, 16 minus 1. We've got 5 bits, the biggest number we can store is 32 minus 1, 2 to the power 5 minus 1. If we've got 6 bits, then the biggest number we can store is 63, 64 minus 1, 2 to the power 6 minus 1. Or if we've got 7 bits, we can store a number up to 127. So we need 7 bits to store a number that can be up to 100 here. So our answer is 7 bits because 2 to the power 7 is 128, would get you the mark. Or you could say 2 to the power 6 is too small, so 64. Or you could say the biggest number that you could store with 6 bits is 63, or the biggest number that you can store with 7 bits is 127. Okay, so your challenge now is to read through question 2 part C and to have a go at each of these questions just here. Let's read through and have a look at the keywords. It says a storage device on the drone records the battery levels for each second while the drone flies. The data is encoded using RLE, run length encoding. So you'll need to go away and remind yourself how that works. You need to choose one of these to say why RLE has been used. The drone can also be operated by Wi-Fi, providing that whoever connects to it enters the right password. And the password is stored on the device using Cipher, probably the worst encryption algorithm known to man, but it's one that we have to know for this exam. Complete the table using a Cipher algorithm. So you need to remind yourself what a Caesar shift is and what this plain text would be if it's encoded using a Cipher with a shift of +3. And then you need to go backwards. You need to work out if that's the original plain text and that's the cipher text, what is the Caesar shift we need. And then also in the next video you'll get the answer to this one. 2 marks here. Security researcher finds an abandoned drone in the garden, and she's able to read the encrypted cipher text, so this text here, by plugging it directly into her laptop and inspecting the data stored in its memory. Even though she does not know the Caesar shift, the number used to encrypt the password, it doesn't take her long to work out the plain text password by trying all the possibilities. We have to explain the maximum number of attempts she will need before guessing the correct Caesar shift. So you need to state the number of attempts, the maximum number of attempts, and say why that's the maximum number of attempts necessary. Okay, thanks for watching. I'd recommend researching RLE run length encoding and Caesar ciphers, and then we'll go through how to get to the answers in the next video. Thank you.